Good morning again, and welcome back to this third lecture on metal forming processes. Until now, we have covered introduction, then classification, then we have covered tensile test, which was for evaluating your different material properties. And we will continue our discussion on this tensile test. Okay, so we have covered nominal engineering stresses. What is nominal stress or engineering stress, and then engineering strain. Today, in today's class, we are going to cover true strain and true strain, true stress and true strain. Okay, so during the tensile test, as we are aware, we are calculating your engineering strain by considering your force and your cross-sectional area, and your cross-sectional area is taken is your original cross-sectional area. Okay, so suppose this is your test specimen, and this is your test specimen. Okay, so you are having original cross-sectional area, suppose AO, and you are applying certain tensile force, say capital F. Okay, so what happens when you are applying, when you are stretching your specimen? What is happening? Its cross-sectional area reduces, and your length of your specimen increases. Okay, so the cross-sectional area, maybe now it is A1, and A1 is slightly less than your AO. Okay, under the action of force, tensile force F. Okay, so how would you calculate your engineering stress? Your stress will be given as F upon your original cross-sectional area. Okay, so this we have studied in our previous classes, or maybe in the physics also, when in the 11th or 12th you might have studied how stress is calculated. Okay, but when we are talking about engineering application of stress, so what you will notice here, that you can see, if you further increase your force, suppose now you have increased force from F to F1. Okay, so suppose F1 is is greater than, sorry, your F1 is greater than F, your initial force. Okay, so again this will reduce your cross-sectional area, and there will be a considerable change in length, and there will be a increase in length, obviously. Okay, so now your cross-sectional area will become A2, and okay, so what you will see, that your original cross-sectional area was AO, then A1, then A2. Okay, and as soon as you keep increasing your force, your cross-sectional area will reduce. Okay, so if you see the actual condition of your this specimen, what is happening? The force, suppose you have applied force F1 on cross-sectional area A1. So what is happening? The actual cross-sectional area which is under the, or which is resisting the force, tensile force, is A1. It is not A0. Okay, so for calculating the stress for engineering applications, what we are doing, we are calculating your true stress. Okay, so how this true stress is given? True stress is given as your applied force, suppose F1, divided by your instantaneous cross-sectional area. Okay, So we have to measure the cross-sectional area of your test specimen after the application of this particular force. Okay. So now in this case, your cross-sectional area will be A1. So this, what it will denote? It will denote your true stress. This will denote your true stress. Okay, so that is how it is written, as your true stress is given as sigma equal to F upon A. Okay, so here A is what? A is your instantaneous cross-sectional area of your test specimen. Similarly, what about strain? We calculate strain epsilon equal to change in length upon original length. Okay, this is what we have studied in our previous classes or previous science classes. Okay, so suppose initially your your length of your test specimen is AO, and after the application of your force F1, the length becomes L1. So how do you calculate the strain? You calculate the strain simply L1 minus LO divided by LO. Okay, so change in length upon original length. Okay, this you have about this stress, or how do you calculate the strain, you are aware from your previous classes, or we have also discussed in our previous lecture also. Okay, so but now we have to also see what is the actual strain, okay, or the true strain on your specimen. Okay, so for calculating the true strain, like your true stress, because for true stress we were calculating your force upon instantaneous cross sectional area. But for true strain, what we are doing, we are taking natural log of your instantaneous length divided by your original length. Okay, so this way we are calculating your true strain, because this ratio, if you increase your length, this value, that is natural log of L upon LO, will increase. Okay, so let us see on the graph how this your true stress and true strain are plotted. Okay, so this is your you can see here, this is your true stress strain curve, particularly this upper portion. Okay, so this dotted line you can see from up to your yield point, lower yield point, your engineering stress strain curve and your true stress strain curve both are coinciding. You can see from O to A to B, B to Y. This up to this portion, your true stress strain curve and your engineering stress strain curve are more or less same for almost all materials. Okay, but beyond point Y, that is in the region of pure plastic deformation, that is from your lower yield point, that is Y, what is happening? Your engineering stress is less. Your engineering stress strain is less as compared to your true stress strain. Okay, this is your true strain curve. Okay, so here you could see that beyond ultimate tensile strength point, that is your stress was decreasing, but in actual the true strain is increasing rapidly. Okay, so at the point of fracture, your true stress is high, but in the case of engineering strain, it is showing that it is lower than for ultimate tensile strength. Okay, so for understanding that the deformation behavior of materials, we have to take consideration of your true stress and true strain in order to predict the actual behavior of your material. Okay, so let us move ahead. I have tried to make today's lecture a bit short. Okay, so maybe we will finish quickly. Okay, so the same curve for the further discussion. Okay, so this is your true stress strain curve, the same curve we have taken. And if you see the properties, if you try to represent this stress strain curve, you can represent using this formula, that is sigma equal to k epsilon n. Here k is your strength coefficient, n is your strain hardening or work hardening component. Maybe you have studied about this equation, sigma equal to k epsilon n, in your manufacturing course also. Okay, you might be aware about these terms. So see this k epsilon n. This is sigma equal to k epsilon n. Okay, so this is your curve, which is representing your true stress strain curve. Okay, this is the equation which is representing your relationship between true stress and true strain. Okay, so in this particular equation, if you try to see the property, take the log of natural log of this equation, you will see log of sigma. Okay, log of sigma is equal to log k, okay, plus log of epsilon n. Okay, so this you can take. I hope everybody is aware how to take natural logs. Okay, so this, since this is the exponent, so this will come here. Okay, from the mathematical properties, we are aware that this term can be replaced as n natural log of n multiplied by natural log of epsilon. Okay, so log e sigma equal to log k. I hope because I'm since I'm tapping on my slide using my mouse, so I hope you are able to understand the term which I am reading. Log e sigma equal to log e, that is natural log of sigma is equal to natural log of k plus n times natural log of epsilon e. Okay, so here you can see this equation looks like the equation of a straight line. Suppose log e replaced by y equal to log k replaced by m. Suppose y. Okay, just a second. Your log e replaced by y equal to m. So n replaced by m, and log e log e epsilon replaced by x, and log ek replaced by c. So you can see that this looks like a equation of a straight line. Okay, so y equal to mx plus c. So so we can conclude that if you take the natural log of your this particular equation, this will yield up, or this should be a straight line. Okay, pi equal to mx plus c. So let us see. This was your true stress strain curve. Here, this is this curve. I am moving my mouse. This is your true stress strain curve. Okay, but when we are drawing, or we are plotting the natural log of this particular equation, that is sigma equal to k epsilon raised to the power n. Okay, so what is happening? If you are plotting natural log of true strain and true strain, it is coming a straight line. Okay, so here you can see this curve, that is a natural plot of natural log of true strain, and true strain is a straight line. Okay, so this is your straight line, and at the point of where your necking is starting, there is a slight slope or decline in your natural log of your true strain. Okay, so your natural log of true strain is increasing after necking, but your natural log of true strain is not increasing much. Okay, so yes. So okay, so what we can conclude from this from this equation? This equation one, that is sigma equal to k epsilon n. It is called as your flow curve. Why it is called as flow curve? Because it depicts the behavior of your material or flow of material plastically in the plastic region. Okay, so this is called as flow curve. It represents the behavior of material in plastic zone. It also represent the capacity for cold hardening, cold strain hardening of your engineering material. Then this we are aware the natural of the logarithm plot of flow curve is a straight line. This we have already explained. Then the slope of straight line is equal to your exponent n. Okay, so the power of epsilon, that is n, it is represented by your exponent of your straight. Okay, so here we can see this, how this exponent n we are calculating. This is given by your slope of straight line. Okay, so this is also we have concluded from this discussion that your slope of straight line is equal to your exponent n. Okay, so let us move about the value of n for your perfectly solid or perfectly plastic solids as well as plastic solid. So what will be the value of n for perfectly plastic solid? So value of n is equal to 0 for perfectly plastic solids, and n is equal to 1 for perfectly plastic solids. For most of the metal, this value lies from 0.1 to 0.5. Okay, so this is about your flow curve. Then how this flow stress sigma is affected? How? Because the metal flow depends on your flow stress. Okay, so what are the factors which affect your flow stress that we will try to understand here? Okay, so there are some material factor as well as some process factor. So we will try to take up these factors one by one, and maybe some of these material factors will be explained in your module 2. I will be explaining some of these points, how these material factors affect your flow stress. These will be discussed in detail. Okay, so in material factor, we the first and important parameter is purity of your material. Okay, okay, so if your material is pure, okay, so then course if there are some impurities, if there are some flows, so depending upon type of impurity, your flow stress is affected. Okay, so how it is affected, whether it is increases or decreases, that we will discuss in coming classes. Then crystal structure we will discuss. Okay, grain size, then heat treatment. So these are the material factors which affect your flow stress. Heat treatment means whether the material is heat treated or not treated. That is whether the material is annealed or not. Okay. Or okay, then process. There are process factors like strain rate. Okay, so how much strain we have applied on your on your metal specimen. Then what is the strain rate, that at what rate we are straining your material. Okay, obviously there is a maximum strain rate exists for each and every engineering material, beyond which if you increase your strain rate beyond that limit, what will happen, instead of straining your material may get better. Okay, it may get straight. Okay, it is like something like that. If you applying a sudden loading, obviously your material get fractured. But if you apply gradual loading slowly, it means your strain rate is slow, and you are able to strain your material. Okay, you can you are able to plastically deform your material. Okay, then the next parameter is your temperature. Okay, so temperature, obviously it has been discussed in previous class also. The in any material forming process, temperature is the important parameter which affect your okay. Okay, so uh, in because temperature is your main parameter. So what is happening, you can see here, with the increase of your temperature, you can see the plot between your flow stress and its effect on temperature. Your flow stress is slowly decreasing with your with the increase in your temperature. Okay, so if you plot your flow curve in it, between it is your true stress and true strain. Okay, so if you try to see this curve, okay, let us focus on your uh, stress strain curve, that is true stress strain curve in your plastic region. Okay, so if you take only this much portion, I hope you are able to see my mouse movement. Okay, if you take this much portion, what you can see, this portion is your representing your true strain and true strain in the plastic region. Take this portion separately. Okay, so because if I will draw on PPT, it will take time. Okay, so if you take that portion, it will come like this. Okay, so here there are few terms which are important and which are needed while predicting your material behavior in metal forming processes. Okay, so your flow stress, we are aware that flow stress is given by sigma equal to K epsilon n. So you can write it as flow stress curve sigma f, or you can say sigma f is given by K epsilon n. Okay. The flow stress curve, we are aware it is based on your true strain and true stress and true strain, and your average flow stress. Okay, during your plastic deformation, it is given by sigma m equal to K epsilon n, epsilon max raised to the power n divided by 1 plus n. Okay, suppose your maximum flow stress is epsilon max. Okay, so then you can calculate your average flow stress using this formula. Okay, so for today, I will stop here. If there are any query, because I want to add certain, more material in your this temperature effect of temperature in metal forming processes. So I will take this lecture in the next week. Okay, so for today, I will stop here. If there are any query, we can take queries.